So it's great to see all of you here at this Heidelberg AI event with Eric Brachmann, who's working at Niantic Spatial as a senior staff scientist. And to give you a general schedule, in the beginning, Eric will hold a talk, and afterwards we will have a scientific discussion, which is moderated by us. And please do not speak immediately, raise your hand, and then we will let you know that it's your turn to talk. The entirety of the talk will be recorded and uploaded to YouTube afterwards. However, not the question round and the scientific discussion afterwards. And for those of you who've not attended a Heidelberg AI event, Heidelberg AI is a student-led initiative which is hosted by the German Cancer Research Center, and we are looking to foster the local AI community. And we are part of an ecosystem where our partners are the LS Unit Heidelberg, the NCT Data Seminar, and Helmholtz Imaging. Heidelberg AI is organized by the people you can see right now on the slide, and all of these are members of the Division of Medical Image Computing, which is led by Professor Klaus Meyer-Hein. Now, let's get back to Eric. So, he studied computer science at the Technical University of Dresden, also did his PhD there under the supervision of Professor Gumholdt and also Professor Carsten Rother, who's now at the University of Heidelberg. Then he was a research associate at the University of Heidelberg. During this time, he had multiple research stays at institutions like Microsoft Cambridge and was nominated for multiple awards and awarded numerous prizes. Since 2020, he works as a scientist at Niantic, nowadays Niantic Spatial, where he's working on the visual positioning system, where his developments went into products like the little-known Pokemon Go and Ingress. He's further active as area chair for conferences like CVPR, ECCV, and WACF, reviews for multiple conferences, and is organizing tutorials and workshops on computer vision. His research focuses on relocalization, post-estimation, end-to-end learning, robust optimization, and feature matching. He has been doing this for a long time now, I think almost 10 years. Examples of this work are RANSAC, short for random sample, of his work are on RANSAC, which is short for random sample consensus, which is commonly used in computer vision for camera localization. RANSAC operates by sampling hypotheses, which are ranked as good or bad based on estimated parameters. Too many parameters and bad hypotheses do degrade the performance. RANSAC, however, is sadly not differentiable, so it cannot be learned end-to-end with neural networks, which makes it really hard to merge it. So, in his own words, he just decided to keep the good parts and throw the bad parts away. He proposed DSEC, where he extended the popular RANSAC algorithm, which makes the hypothesis sampling selection differentiable. And then he further proposed neural-guided RANSAC, where the hypothesis search is learned, which lets the algorithm learn arbitrary task losses. Both works have left a great impact on the field, and I'm really happy that we have you here, Eric. And as a fun little anecdote, which I heard from Professor Carsten Rother, is that there exists a recording of the CVPR oral talk from 2017 by Eric, which is still used to this day by the Computer Vision Lab in Heidelberg for educational purposes as a blueprint for what a great talk in computer vision is supposed to look like. And now, without further ado, I would like hand over to Eric.
Thank you for the very, very kind introduction. Let me share my screen. Okay, we tried it before, but still, are you seeing the slides?
Yes.
Are you hearing me all right as well?
Yes.
Very good. So we can start. Yeah. So the talk will be about structure from motion. There will also be a little bit of DSEC in here and RANSAC as well. There will be pushing of boundaries, and there will also be a bit of machine learning. Let's see how it goes. So you heard the introduction already. You have some contact information here as well. I'm moderately active in social media, so you can connect there if you like. And as you have heard, I've been in research for a bit more than 10 years now. I did my PhD in Dresden. And in the beginning, I was working on object pose estimation. So the problem is you have an image and you have a pre-defined object, a pre-scanned object, and you want to find it in the image and you want to estimate the orientation and the position of that object. A bit later, I switched towards a related task, which is called camera relocalization, and we will hear a lot about it today. It's related because the object that you're interested in is now the whole scene, and you want to estimate the orientation and the position of the scene, which means you want to estimate the orientation and position of the camera relative to the scene. And basically, I still do that today. I work on this task for almost 10 years now, and it never became boring. There was always something interesting to do. So throughout working on this task, I worked on ransack, differentiable ransack, robust optimization. I worked on feature matching. I worked on reconstruction. I worked on uncertainty estimation, all kinds of different flavors of parts which basically go into this pipeline which tries to solve this task. So it has been a quite interesting task which did not get boring. After my PhD, I did a postdoc in Heidelberg. So PhD was with Stefan Gumholdt and Carsten Rother, as you have heard. And Carsten moved to Heidelberg, and I did my postdoc with him in Heidelberg. Although I was not in person in Heidelberg, I was staying in Dresden, but I visited several times. So I know that Heidelberg is a very nice city. Right. And then after my postdoc, I joined Niantic, which you might know from the games, Pokemon Go and Ingress and Monster Hunter now. But recently, the company was split into two parts. The games were sold to a company called Scopely, and the tech platform part became its own independent startup, which is called Niantic Spatial. And that kind of makes sense because the technology was anyway already powering the games, but it was meant to be more than the games, and now it has its own home in this startup. So the goal of Niantic Spatial is to invent and build the next generation of maps. And as part of this tech stack that we have, we also offer the so-called visual positioning system. The idea is that you can take out your phone or any other device and you take a picture, and the system is able to tell you where you are to the centimeter and also how you're oriented in the world to the degree. What you see on the slide is a heat map of density of locations where this system already works. So you see we have nice coverage in North America and in Europe, also in Japan and some other places, and also in Heidelberg. You do not have to walk far to get to a place where this system would work. And if you are at such a place, and you are a developer, you can build experiences like this one. This is an AR experience, which means that virtual content is aligned with the real world as precisely as possible to create a sense of immersion. And this is basically what I'm working on and what we will be talking about today. What methods power such experiences? In the academic context, the task that we are trying to solve, and I have mentioned it already, is called visual relocalization. It consists of two parts. You first have the mapping stage, where you build a scene representation. So you collect images and you reconstruct a 3D model of the scene, which is the map of the scene that you want to relocalize in. One question, when I have videos like this, are they displayed correctly? Because I think I forgot to click optimize for video when I shared my screen.
So
But
it just worked.
It just worked. Okay. If you see videos, if the organizers see videos are poorly represented, I can reshare. But let's try it like this. Okay, so we have the mapping stage where we build a 3D map from images, and then we have the relocalization stage. So a new user, much later maybe, goes to that location and takes a picture. And now we want to estimate the camera pose, we want to register this image in the map that we have previously built. So this talk will focus on the first stage, or the mapping stage. How do we build 3D maps from images? And again, in the research context, this particular problem is often called structure from motion. How do we estimate camera poses and the structure just giving a set of images? And this is a very well-researched problem. We have good methods for this for at least 20 years now, 25 years maybe. And very good tools today readily available to solve this task. Colmap, if you heard of that. And the classic way to do this is the following. We have our set of images and we select two to start the reconstruction. We select two images and then we find feature points and establish correspondences. So we're looking for key points which are representative and distinctive in the images, which we can match across images. And when the matching succeeds, it gives us 2D to 2D correspondences between these two images. And using projective geometry, given the correspondences, we can estimate the relative pose between these two images, the translation and the orientation of one image relative to the other. And if we have the relative pose, we can triangulate the key points that we have matched. So we get the points in 3D originating from the 2D to 2D correspondences. So this is the seed of the reconstruction. Now we go on. We select a third image. We extract features again, and we match them against the other two images. And if we find matches, we can register this third image into the scene, and the third image might allow us to triangulate more points. And if we repeat this with all the images in our set, we basically get all the camera poses, and we get a 3D point cloud of the scene, which will serve as our 3D map. So this has been working very well for a long time. We have good tools to do this, but still there are limitations and room for improvement and opportunities for research. And in this talk, I want to focus on a particular dimension of limitations. And that is the following. These tools like Colmap to do structure from motion, they work best with a particular amount of images. So I would say they work best if you have in the range of hundreds of images. If you have hundreds of images of your scene, that means you have good coverage, you have seen mostly all of it, and the viewpoint changes from image to image, they are not too extreme. So you can do the feature matching quite reliably. So that is basically the ideal case for traditional structure from motion. A few hundred images, that's great. In the talk, I want to see what happens if you have much fewer images or what happens if you have a lot more images. Let's go to the left first. What happens if you have very few images? So let's say you just have a handful or maybe just 3. Well, the problem immediately gets much more difficult because the viewpoint changes from image to image are more extreme and the feature matching gets much more difficult. It's more difficult to describe local points in a way that you can find them in an image which was taken from a much, much different perspective. But it's today a very active research topic. Many people are working on this, and in the last 2-3 years, we have seen tremendous progress based on learning-based models. So very active research topic. But I want to know what the limit is. So how few images can it be? Can it be 3 images or 2? It cannot be 0 images, right? Because if you want to visually relocalize, you basically have to have something. It has to be at least 1 image. So is 1 image enough? Can we relocalize based on 1 image? That is basically my question. And well, if you want to do something like visual relocalization, you will always have at least 2 images. You have one image, which is the map. Let's say, well, let's call it the reference image. But you will always also have the query image of the user, which you want to relocalize. So in this setting, with just one reference image, Visual relocalization means estimating the relative pose between two images, the reference image and the query. And if you recall what I just told you about structure from motion, this is actually also how we do structure from motion in the beginning, right? We start with two images, so we can just do that now as well. We try to find correspondences between the two images, and that allows us to estimate the relative pose between them, but with a catch. Because with geometric reasoning, with projective geometry, we just get the relative pose up to scale. We do not know the distance between the cameras. We know the relative rotation. We know the direction of the translation, but not the distance along this direction. You can imagine it like this. Just from the images, it's very hard to tell whether this is actually a real fountain or whether it's a miniature replica, a toy. From the images itself, you cannot really tell because the images would look the same in both cases. And that's why there's this scale ambiguity from the images alone. So the question now is, does it matter for an application like augmented reality? Well, unfortunately, it does matter. So let's assume we have such an application. Here we have two users in the same place. And the first user on the left, they place virtual content in the scene. And the second user wants to look at it. So what we need to do is we need to take the virtual object and project it into the second image. But if we do not know the scale of the scene, if we do not know the distance between these two cameras, then the virtual asset could be anywhere along this line. And that is, of course, bad. So we need to know the scale. So we cannot solve it with projective geometry, but we cannot solve it with heuristics. And heuristic means we can solve it maybe with machine learning. So for example, we could take depth estimation networks. Networks which predict for each pixel the depth, the distance to the camera in meters. Such methods exist. If we use these depth estimation networks, the correspondences which we find between these two images, they are not 2D 2D anymore. They are now 3D to 3D. And that means that we can estimate the relative pose between the two cameras up to scale. We basically get the scale estimate from the depth estimation networks. And these depth estimation networks themselves, they rely on heuristics. So maybe they look at the grass, they infer, oh, it's a real fountain, it's not a toy, and there are trees in the background, which gives them a signal about the distance, and so on. This is how this works. This, of course, is a schematic, but it actually also works for real. So here you see a real example where we have a reference image on the left and where we have a few query images on the right, and you see correspondences predicted by an off-the-shelf feature matcher, superglue in this case. And then we can also apply a depth estimation network for these two images, and we get depth maps. And if we put these together to get 3D correspondences to estimate the relative pose, we can actually get a scaled estimate of relative poses between these two images. So now from the method side, this is very unexciting because we just took two off-the-shelf methods, we put them together, and now we can estimate the relative pose between two images up to including scale. So what? But from an application point of view, this is very exciting because it means you can just go to a new place. You can take a single image and that's it. That's your mapping stage. Mapping is done. You don't have to collect multiple images. You don't have to walk around. You don't have to upload anything. You don't have to reconstruct anything. One image done. And then you have a scene agnostic machine learning model. In this case, this is our depth estimation model. And it defines a scale metric space around your first image. And within this space, we can register new images. We can relocalize new images just based on the single reference frame. So from an application side, we were very excited that this works. And whenever you want to excite other people, you have to give it a name. So we call this map-free relocalization. The task of map-free relocalization is you have to estimate the relative pose, including scale, between two images. This was an ECCB 22 paper, and many people worked on this. Because if you want to excite people, you not only have to give it a name, you also have to make it a challenge. So we made it a challenge. We collected a large data set, at least at the time it was large, with a few hundred scenes of for support of this task. So you get reference images, you get query images, you get scale-metric ground truth between those, and you can test your method, how well your method works. You get a sizable training set to train whatever you come up with. You get a validation set as well, and you get a private test set. So you have to upload your results to a server to see your scores. And the data set is quite challenging. So I showed you the example with the bear, which was working all right. But we have stuff like this in the data set. And in the beginning, it also looks all right, right? We have the statue here. In the beginning, query and reference are in the front of the statue. We find many correspondences. The depth estimation does work. Therefore, our pose estimate also looks solid. But now in the scene, the user that took the scan actually went around the statue. And at some point, you are behind the statue. The reference shot is from the front. So you have to do front to back feature matching, which is very, very challenging. Your feature matcher breaks down. There are no co-visible surfaces anymore. And without correspondences, you cannot estimate the pose. And we have many such cases in this data set and other challenges as well. So it's really difficult. There's an online leaderboard, so if you want to try or if you're just interested how people address this task, give it a look. It's up and running. And you can submit your own results based on the data set that you can also download. So we did this challenge or this benchmark in 2022. And afterwards, when we sat down and we thought, okay, before we were just taking off the shelf stuff, putting it together to see how well it works. But now we want to really sit down and come up with a solution ourselves. And the solution we came up with is called Mickey. This was a CVPR 24 paper. And the idea behind Mickey is relatively simple. So we stick with the original strategy of feature matching and pose estimation, but we do everything in 3D and in metric 3D. So it looks like this. We have two images where we want to estimate the relative pose, and we extract key points, but we don't extract 2D key points. The network predicts key points in 3D camera space and in metric space as well. And for each 3D key point, you also get a high dimensional descriptor, as with traditional methods you would also get. So the descriptors you can use for matching to get correspondences. These correspondences are now 3D, and they are metric. So if you apply your pose solver, you get a relative pose, including scale, in metric units. So before we had these two methods, depth estimation method to the feature detector. And maybe you see that the only thing we did is we put them together. So we merged them in a single model, and now we can train them jointly. We can train them together. And this is actually where also the magic happens. Because how do you train systems like this? Normally in machine learning, you have your forward process, right? You have your network, it predicts something, you define a loss, and then you backpropagate through it. And we want to do the same here. The only problem is the actual estimate that we are interested in is the relative pose. But if we want to backpropagate the relative pose error back to the network, we have to go through feature matching, we have to go through the RANSAC algorithm, we have to go through the pose solver, and so on. And this is actually difficult because these steps involve discrete actions. For example, in feature matching, either you match key point A or you match key point B. If you have a network and you want to tell the network via gradients to not match A, but to match B, it's not a smooth transition. It's just either you match A or you match B. And it's the same with RANSAC. In RANSAC, you create multiple hypotheses about the pose, and then you select the one with the highest support. This is also a discrete selection. You select the best pose within the RANSAC algorithm. It's challenging, but it's not impossible. We have worked on this for a while. So we have differentiable RANSAC, we have neural gated RANSAC, and we had a paper called Reinforced Feature Points, which basically explains how to make the feature matching differentiable. So all the parts are there. We just have to put them together. And this is what we did in the McGee paper. Um, I will not explain it in detail because it's a multi-stage process of multiple discrete actions where we have to propagate through. But I want to give you the gist, at least, of how this works in general. So what you will see now is a simplified version of how training works in the McGee pipeline. So we want to learn 3D to 3D to establish good 3D to 3D correspondences. But as I said, they are discrete. And you have to make them soft somehow. You have to make it smooth such that in gradient optimization you can optimize it. So the first step to make it smooth is to say, actually, I assume that all correspondences exist. All key points match to all other key points. All correspondences are there, but they have different probabilities. And the probabilities are derived from their descriptor distance. So if you have two key points and their descriptors are close, then they are similar, then the probability of these key points matching is large. And if you have two key points with very different descriptors, then the probability of these key points matching is small. And this gives you a way to optimize matching, because if you want to tell the network to not match A, but match B instead, you basically just say reduce the probability of matching A and instead increase the probability of matching B. And this is basically the idea. But how do we get poses now to optimize it actually with a pose loss? So a simple version of this would say, well, I just sample matches from this probability distribution. So individually, I select matches with high probability, but randomly, and I get a random sample of discrete matches. And from this discrete set of matches, I can estimate a pose. And I do it again. I sample again. This time I will get, because I randomly sample, I will get a different set of correspondences. And therefore, I will get a different set of camera poses. And I do it again and get a third set of matches and a third camera pose estimate. And I do this many times in reality. And then I can compare all my different samples to the ground truth and compute a loss. And this loss I can now backpropagate to my matching probabilities. And what happens is if I have a good pose hypothesis, then I want to increase. I obviously had a good set of matches and I want to increase the probability of these matches. And if I have a bad pose estimate with a high loss, then I want to decrease the probability of this particular set of samples that produce that loss. And this shapes the probability distribution of matches, and in turn, it shapes the descriptor space. Because whenever I increase the probability of a match, I pull together their descriptors, and I also refine the key points to be more to yield a more precise pose estimate. And for bad pose estimates, I push the descriptors apart and I don't care about the position of the key points. This is basically the idea of how McGee training works. All right, so in theory, it should work, but did it actually work? Yeah, I'm happy to tell that it did. And just by supervising the network with relatively weak signal, just by supervising it with relative poses, the network figured out the 3D structure of the scene and predict metric 3D key points without direct supervision. We never had depth maps or anything. It still predicted the structure of the scene in metric space and is also able to match relatively extreme viewpoint changes. So in this case here, we go to 90 degrees from the front to the side, and the network can still estimate the relative pose between them and match features, which was quite nice to see. All right, that's the first part. So we looked at structure from motion with basically representing a scene just with very few images and in fact just one. And we still can do tasks like visual relocalization. We know that it works with hundreds of images because the classic approach works with hundreds of images. So what happens now if we have more images? What happens if we have thousands of images or even more than that? Well, of course, you can still apply the classical approach, right? If it works with hundreds of images, it will still work with thousands of images. The problem is it will be slow, at least if you do it naively. And why is it so slow? The problem is that the classic way of doing structure from motion, it relies on optimizing over 2D to 2D correspondences, which means it relies on doing image to image matching. Now, if you get a set of images like this, upfront you know nothing about it. You do not know how they are related and which of them are actually matching, where you can actually find key points. So what you have to do is just to try all combinations. With 4 images, of course, that's no problem. With 8 images, yeah, whatever, right? Still no problem. But with 16 images, it was already quite difficult for me to draw all these lines for the figure. And with 100, 200 images, that's the amount which where it's still computationally effective or even efficient to crunch all through these image pairs that you get. But if you get 1,000 images or even 10,000 images, then you really suffer from this quadratic explosion of looking at all these image pairs. Now, I don't want to make the impression that this has been an unsolved problem for a long time. This is a conceptual problem, right? This was a problem from the start. And I said that we have this for 20 years now. Of course, people looked into this and people came up with good solutions how to deal with this in the image to image matching world. And I would say the most practical solution is to not do exhaustive matching, to find a way to only select promising image pairs and early reject image pairs where you will anyway not find matches to tremendously reduce the amount of image to image matches that you have to process. So this is the standard way to deal with this problem. But it's still a challenge, right? Because what you're trying to do is you try to come up with a cheap method to look at your image pair and tell whether it's worth it to apply your feature matcher, which is too expensive to apply to everything. And well, that's difficult because in the end, you're interested in a method that tells you what is the benefit of me matching these 2 images in my reconstruction at the end. That is a difficult problem. So we were interested in solving this problem completely differently. We try to solve it by optimizing the 3D geometry directly from the individual images without looking at image pairs at any stage. So the graph that you see here, it simplifies tremendously, right? Instead of this many lines across the pairs, you just have a star structure now. Each image is basically connected to the scene. So how does this work? In order to explain how it works, I first have to explain a different algorithm on a simpler problem. And the simpler problem is just optimizing the geometry given camera poses already. So we assume we have a set of images and we have their camera poses, and now we want to somehow represent a scene. And one way to represent the scene is called scene coordinate regression. This is a visual relocalization algorithm, and I will explain it now. So scene coordinate regression follows again this traditional pipeline of feature matching a little bit, where we said, okay, you can extract key points and then descriptors, and you match them across images, and from these correspondences, you can estimate the pose. Scene coordinate regression is quite similar. The only difference is that you merge the steps of feature extraction and feature matching. You do not do a discrete matching based on descriptors. Instead, you directly regress correspondences with a neural network. Let's look at how it looks like. So we have this query image, and we want to relocalize it in a 3D scene, which I visualize here as a point cloud. And we want to do this with a neural network. The neural network is trained for this particular scene. That means it's trained with images of this scene, with known camera poses also of this scene. And during training, the network builds internally a representation of the scene. It builds a map, but the map is implicit. It's encoded in the network. So to say, the network itself becomes the map. The task of the network is to predict scene coordinates. Imagine the room that we have here, it has its own reference space. It has its own coordinate frame that it lives in. And each point in this room has a unique 3D coordinate in this reference frame. And we can visualize them by mapping the by mapping the XYZ coordinate of the scene coordinate to the RGB cube. So each point in the room has a unique color. And basically, the network tries to predict these scene coordinates. For every pixel, it predicts where this point lives in scene space. And this gives you a dense correspondence field from 2D to 3D, which we can again put into a pose solver and estimate the pose of the query image with respect to this scene. All right, so how do we train it? I said that we have images of the scene and poses. Unfortunately, we do not have the geometry of the scene. For example, we do not know the depth of all these pixels. So if we had depth, it would be simple. Then we could calculate ground truth scene coordinates and just have an L2 loss between the ground truth and the prediction. But we don't have that. We only have the pose. But what we can measure is a reprojection error. And this is the following formula. I will walk you through it. We have the 3D coordinate, which is predicted by the network for pixel I. And we have the camera pose of the associated mapping image. Assuming we know the intrinsics of the camera, we can project the 3D coordinate back into the image, which gives us a 2D location. And this 2D location should be the same as the pixel location that the coordinate was predicted for. Another way to put it is the scene coordinate should be self-consistent with the ground truth camera pose. Should land back to where it was predicted for. Some kind of cycle consistency. It's not cycle consistency, but it's a self-consistency, so to say. There's one problem with this formula. Any scene coordinate along the pixel ray would satisfy this formula. The depth of the scene coordinate is ill-defined. But it turns out in training, this still works. Because in training, it sees multiple views of the same scene and therefore tries to converge to a multi-view consistent solution. And the only multi-view consistent solution is to put the scene coordinate at its actual depth. Right, so through our training, the network actually learns the geometry of the scene without image-to-image matching, without ever looking at pairs of images. It just sees one image after another randomly. And then afterwards, after you train the network, you can use it to relocalize. So if you have a new image, you can put it into the network, then it will predict scene coordinates, you can estimate the pose, and you can do that very precisely. As you see here, the pose estimates are very accurate. There was one main problem with this kind of approach. You need to train a network per scene. If you get a new network, if you get a new scene, you need to train a new network. And training these networks took 1 or 2 days when I did it first. And that's bad, right? Because if you get a new scene, if you want to scale this at large, many scenes, thousands of scenes, you have to spend so much compute because you have to train a network per each new scene. And that's not great. But we came up with a solution that was in CBPR 23 with the ACE algorithm. ACE just means accelerated coordinate encoding. And the only purpose here was to make it faster. How can we train this very quickly? And the idea in a few words is before we were optimizing a whole CNN image by image, one image at a time. And with ACE, we switched to optimizing an MLP at the patch level. So each training batch consists of randomly sampled patches throughout your whole mapping sequence, which means that in every training iteration, the network is supervised with multiple cameras, potentially thousands of cameras at once, which gives you a very good training signal, and this converges much faster. How much faster? Here you see a side-to-side comparison. On the left, there is the old image-based optimization, which takes 15 hours to converge. And on the left, on the right, you see ACE, which does this patch-based optimization, and it converges in 5 minutes to the same accuracy. So you're 2 orders of magnitude faster, and at the end you can relocalize with the same quality. You do not lose anything; you just gain speed. Right, so that's great, especially if you want to build a worldwide VPS. That's great because ACE is actually deployed in the VPS servers. And if you want to cover many places, it makes a tremendous difference whether your network takes 1 day to train or whether it takes 5 minutes. So up to date, we have trained 70 million ACE networks, probably more by this point. And well, it wouldn't be possible if each network takes a day to train. You couldn't pay that amount of compute. All right. Great, right? But we wanted to do something different. We wanted to do structure from motion. So we are back to this task where we say, well, actually, we know now that we can train an ACE network from posed images, all right. But what we actually wanted to do is to do it without the poses. So where do the poses come from? So we have the scene here. We have a model, a ACE model, which we have trained on a set of images with poses. And we know that it's a visual relocalization algorithm, which means that if we get a new image, one without a pose, we can apply our network. We get a scene coordinate prediction, which means we have 2D, 3D correspondences, and we can feed it to our pose solver to estimate the camera pose. Now, the idea to make it a structure from motion pipeline is to have it estimate its own poses. So maybe we don't need the red poses because we can estimate it with a model that was trained on the blue camera poses. And maybe we can also get rid of these 3 poses by estimating them from a model which was only trained on these remaining poses, and so on. Maybe we can train the model incrementally, starting with a model which was just trained on a single image. So would that work? Can we train an ACE network on a single image? Well, first question is, what is the pose of the first image? Well, we can set it to identity. That's fine. Second question, can we train an ACE network with the identity pose in a single image? Well, not using the reprojection error, but there's an easy way around it. We just, for the first image, apply a depth estimation network. And the depth estimation network tells us the geometry of this very first image. We will never need a depth estimation network again. Just for this very first image, we get a point cloud from a depth estimation network and overfit the first relocalizer to this image. The second question is, well, now I have my first model, but what is the second image that I add to the reconstruction? If I just have a set of images and I choose poorly and ACE estimates a bad pose, will the reconstruction recover from that? So let's try it, right? Let's estimate a terrible image. This image is terrible because it's from the other side of the truck, which the method has not seen yet. So it will not be able to predict anything plausible. It will just predict garbage. And but we do not know. So we just feed it to our pose estimator, and the pose estimator gives us a pose. But the pose is also garbage. The question is, can we tell? Can we tell whether the pose estimate is garbage? And luckily we can, because we can check how consistent the pose is with all the different thousands of correspondences that the network predicted with all the scene coordinates. And it turns out that it's pretty reliable that a low inlier count, a low self-consistency means that the pose estimate is bad. And this whole process is very fast. We can check this very quickly. So whenever we have a model and try to add more frames, we just try all frames and see what already works, what relocalizes. If there's a low inlier count, we reject the pose, we cannot use it. And whatever works, we retrain the model on. So this is the ACE0 algorithm. ACE0 because it builds on ACE and trains it in a self-supervised way without poses. It estimates its own poses. And it was described in this paper here, pretty recent, from ECCV, scene coordinate reconstruction. So in the end of the talk, I just want to show you how ACE now actually reconstructs a scene. I was showing you schematically how it works, but now let's look at a real example. So, and we use this truck here, and I motivated ACE by saying we want to do it for thousands of images, 10,000s of images. So let's do that. Let's reconstruct this truck from 7,500 images from these from the sea. So we start with a single image. We randomly select a single image, we apply our depth estimation network, and we overfit an ACE network to this first depth map to get the first relocalizer. And then we check all the 7,500 images and see what we can relocalize. Every pink frustum is rejected. Every green frustum, maybe you see a few green ones, they are accepted with a high confidence. And the most estimates are yellow. That means they are accepted with a low confidence. And they seem quite noisy, scattered somehow. They don't look like good pose estimates. So what we need to do in the next training iteration, when we retrain the network, is we also need to refine those poses. And we can do that quite easily by just backpropagating the loss also to the camera poses. That's enough to refine them. And now you have a second relocalizer trained on more cameras, and it's able to estimate more camera poses, and you can do this in a loop until you have relocalized all the images. And this process takes 1 hour on a single GPU to get the camera poses of 7,500 images. And that's pretty fast because if you do it with exhaustive image-to-image matching, you would have to wait for a lot longer, probably a day, maybe more. All right, in the end, we get some camera poses. You can do stuff with it. So if you have camera poses, for example, you can train Gaussian splats of it and then feel good about how pretty the results are. So that's always nice. And you can try it yourself. The code is available. So you can give it a video or images that you collected, and it will reconstruct the scene. It also gives you the intrinsics, and you can also train Gaussian splats and look at them and feel good about it. Right. So that's basically everything I wanted to talk about today. Thanks for sticking with me. So we looked at what happens if you have just a single image to represent a scene. In this case, we would do map-free relocalization. And we have looked at what do we do when we have thousands, 10,000s of images. And I presented A0, which is an alternative paradigm of how to do structure from motion. Okay, that's it. Thank you so much. And I think now is some time for questions.